Hello everyone, and thanks for watching Edupedia World Videos. In this video we'll start learning Newton's laws of motion, which form the foundation for all of mechanics which you're going to study in the first 5 units. Up till now we've seen two separate aspects of motion, kinematics and dynamics. Kinematics is simply the study of motion of a body. It is not concerned with the cause of motion at all. We've seen this when we studied motion in 1 dimension or 2 dimensions, which could be extended to 3 dimensions. We saw relative motion and some concepts of kinematics as circular motion. In any of these cases, we were not really concerned with why the body is moving the way it is. When I said a body is moving in a circle, we were never really concerned with what makes the body move in a circle. Or when I gave you a question such as a body moves on a line with x is equal to 5t cubed, and what is the velocity at 2 seconds. We were never really concerned with why the body is moving such that x is equal to 5t cubed. We'll change that now and we'll start studying dynamics, which also involves the study of the causes of motion of a body. The causes of motion are called forces. And there are 4 separate types of forces, and this is it. This is the complete list. There is no fifth force that has ever been found, and every force we know of can be grouped into one of these 4 categories. These 4 forces are electromagnetic, gravitational, strong nuclear, and weak nuclear. So let's talk a little bit about them. The electromagnetic force is a force which acts on bodies by virtue of a property which is called its charge. Now there are many different types of fundamental particles in nature, but the only ones which will be important to us are protons, electrons, and neutrons. The charges given to them are positive, negative, and neutral. The magnitude of the charge on a proton is 1.6 multiplied by 10 to the power minus 19 coulomb, but we don't need to know any of that in detail. We'll study electromagnetic forces once we reach electromagnetism. So these are the separate particles, and protons have positive charge on them, electrons have a negative charge on them. Now, the property of electromagnetic forces is that like charges repel each other and unlike charges attract each other. That gives us the direction of forces. The magnitude is given by K Q1 Q2 by R square, where Q1 is the charge on the first particle, Q2 is the charge on the second particle, R is the distance between the two particles, and K is a constant whose value is equal to 9 into 10 to the power 9. Quite a large value. Compared to this, gravity has many similarities but many differences as well. The difference is that every object has a mass, and just like charge is the property which causes objects to attract each other by an electromagnetic force, mass is the property which causes objects to attract each other by a gravitational force. And the force between two masses is given as G m1 m2 by r square. Again, m1 is the mass of the first particle, m2 is the mass of the second particle, r is the distance between the two particles, and g is the universal gravitational constant. And the value of g is 6.67 into 10 to the power minus 11. Now we see a very major thing here, which is the constant for the electromagnetic force is very large compared to the constant for the gravitational force. And this signifies something important, which is that in nature, electromagnetism is a much stronger force than gravity. So on a list of magnitudes of forces, we can say electromagnetism is much greater than the force of gravity. This is not the constant, by the way. This is the name of the forces. And we can actually calculate this. If we take two protons at a certain distance, the gravitational force between them will be G m1 m2 by r square. And the electromagnetic force will be K q1 q2 by r square. If we take the ratio of them, it comes out to be approximately 10 to the power minus 41. This is the gravitational force compared to the electromagnetic force. So we see that gravity is a very small force. How do we ever observe it then? Well, if you start adding objects together, and if those objects are neutral, the number of protons will be equal to the number of neutrons, but the mass will keep on adding. For example, two protons And for example, if you take two hydrogen atoms which are neutral, they will have almost zero electromagnetic force but a very small gravitational force as well. As you increase the mass, as you take two big containers of hydrogen, then the protons is still equal to the number of electrons. So they are still electrically neutral and the electromagnetic force between them is quite small. But as we start adding more mass to hydrogen, its mass increases, and because of that the gravitational force starts increasing. So if we take, for example, the Earth and the Moon, both of them have a very large number of protons and electrons, but both of them are electrically neutral almost. So they have a very small electromagnetic force between them. But since mass always keeps on adding, remember we have positive and negative charges, but we do not have positive and negative masses. Mass is only positive. So the masses keep on adding, and when we have such big masses like the Earth, the Sun, the Moon, that's when gravitational force becomes overwhelmingly larger than the electromagnetic force, and that's when gravitational effects become important. So these are the two forces. There are two other forces which I talked about. So let's look at the strong nuclear force. If you look at a nucleus, it's combined of neutrons and protons, and around this the electrons revolve. So the neutrons are electrically neutral and the protons are positively charged. So there should be a net force of repulsion within that nucleus. But still the nucleus does not blow apart. The nucleus of hydrogen and helium, for example, are stable particles. So why does this happen? The reason is that there is an attractive strong nuclear force between nucleons. And nucleons is just another term for the combination of the set of neutrons and protons. So apart from the electromagnetic force and the gravitational force, all neutrons and protons exert on each other a strong nuclear force which is attractive. But this force has a very specific property, which is it has a very large magnitude for distances between the particles smaller than 10 to the power minus 15 meters, which is also called 1 femtometer. But it is negligible if the distance becomes approximately, these are approximate values, 10 to the power minus 15 meters. And if you look at a nucleus, generally a nucleus has the size of the order of 10 to the power minus 15 meters. So once two protons or two neutrons or a proton and a neutron come together that close, the strong nuclear force becomes overwhelmingly more dominant than the electromagnetic repulsion between two protons. And this is why a nucleus remains stable. Of course, if you were to expand a nucleus slightly, then the strong nuclear force between them would start decreasing, and there would be a point when the electromagnetic repulsion between protons would dominate. It would become greater than the strong nuclear force between protons and protons or protons and neutrons, and at that point the nucleus would burst apart. So this is a very specific property of strong nuclear forces. So we've seen gravitational force acts between all particles. The electromagnetic force acts between particles which have a property called charge, and this property is in protons, electrons, some other particles as well, but not neutrons. The strong nuclear force only acts between nucleons. So the strong nuclear force will act between two protons or two neutrons, or a proton and a neutron, but not between a proton and an electron. Remember this, the strong nuclear force is only between two nucleons, and for our purposes nucleons can be thought of as just protons and neutrons combined. Finally, there is the last force, which is the weak nuclear force, and that force is responsible for radioactivity. So we know from experiments that a neutron can actually convert into a proton and an electron and emit another particle which is called an antineutrino. You don't need to worry about the details now, but such reactions do not occur because of the strong nuclear force, because the strong nuclear force acts between two nucleons. It does not act inside a nucleon. So there is another force which is called the weak nuclear force, and it acts at distances even smaller than 10 to the power minus 15 meters, and it generally only acts within a particle. The range of the weak nuclear force is such that it can act between the center and the end of a neutron, for example. And this is the force which is responsible for reactions like this, and it is responsible for many other phenomena such as radioactivity. right? So these are the four forces. By the way, one small thing, when you look at the gravitational force between the earth and an object on the surface of the earth, that would be GMEM by RE squared, where ME is the mass of the earth and RE is the radius of the earth, right? And this particular quantity GME by RE square is also given another name. It's called small g, which is the acceleration due to gravity, and its value comes out to be 9.8 meters per second square, right? So the net force on an object on the surface of the earth comes out to be mg, where m is the mass of the object and g is just another name for this quantity, which is capital G me by re square. So from now on, whenever I say that the force acting on an object is mg, I am really talking about the gravitational force, and small g is just another name given, so that instead of writing g me by re square all the time, we can just write small g and we know what it means. So the acceleration due to gravity, you know how to calculate it now. It's capital G me by re square. Right. So in this course, we'll only look at strong nuclear forces and gravitational forces. In this course we'll only look at electromagnetic and gravitational forces. Strong nuclear forces and weak nuclear forces, they come under college level physics and we'll not deal with them. We'll deal with gravitational forces when we come to gravity, and once you reach the next class in 12th, you start learning electrodynamics, and that's when you'll see electromagnetic forces. So let's look at a little bit of the history of mechanics and how we came to the point where we are at now. Aristotle was one of the earliest Greek philosophers, and he postulated something which was considered to be true for a long time after that, and that was that a force is required to move any object. This statement is quite a deep statement, so we need to understand it. This statement essentially says that the natural state of an object is rest. Every object wants to remain at rest all the time. And if you want an object to not be at rest anymore, you have to apply a force on an object. And this seems natural enough. If we have a pen on a table, for example, the pen is not moving. It seems to us that the natural state is at rest, and when we push the pen, it starts moving. But what we see is, generally, when we stop pushing the pen stops moving. From that, the conclusion Aristotle made was that to keep a pen moving, you have to keep applying a force to the pen. And the moment you stop applying a force to the pen stops moving. But this had a small error, which is that this assumes that there was no other force acting on the particle. Whereas in fact, when you push a pen on a table, the table exerts an opposite force on the pen called friction. I'm sure you've heard the term before, and we'll deal with it in more detail after Newton's laws of motion. So needless to say, Aristotle was not correct. Galileo came 1500 years after that, and he postulated a very different statement. He said that a force is required to change the state of motion of a body. He did not say that the natural state of motion of a body is rest. In fact, he claimed that the natural state of motion of a body is to be either at rest or in motion, whatever the state it was before. So Galileo postulated a term called inertia, and he said inertia is the property of a body by which it wants to maintain its state of motion. So if a body is moving with a speed of 0 meters per second, that is, it is at rest, then it wants to stay at rest. If a body is moving at a speed of 2 meters per second towards northeast, then it forever wants to move at a speed of 2 meters per second towards northeast. If a body is moving at 10 meters per second vertically upwards, then it always forever wants to keep moving with a speed of 10 meters per second upwards. So an object always wants to conserve its natural state of motion of a body, and if we want to change that state of motion, then we have to apply a force. So this statement says that once a body is moving with a speed of 2 meters per second towards north, then the state of the body is moving at 2 meters per second towards north, and as long as we don't apply any force, it will try to preserve its state, which is it will try to move with a speed of 2 meters per second towards north. And if we want to change that, if we want to bring it to rest, or if we want to change the direction or the magnitude of the speed, then we'll have to apply a force. Newton came many years after this, and he is considered by many to be the father of modern science. He by the age of 25, had made numerous contributions in many wide fields in both mathematics and physics. He is considered to be one of the founders of calculus, and not only that, he contributed to the fields of optics, motion, gravitation, sound, and many more. He was the one who packaged all our understanding of motion at the time, this is the 16 or the 1700s, into 3 laws. And these 3 laws, which are called Newton's laws of motion, are the foundation for all of mechanics. And everything we are going to learn for the next few videos will ultimately be derived from Newton's 3 laws of motion. So let's look at the 3 laws. The first law of motion says that a body will remain in a state of rest or uniform motion unless and until an external force is applied. This is just another way of saying Galileo's postulate, which is that the natural tendency of a body is to maintain its current state, and to change its current state, a force is needed. So if the current state of a body is at rest, then it will remain at rest until a force is applied. And if the current state of a body is uniform motion, then it will stay in uniform motion unless a force is applied. The second law of motion is that the net force on a body equals the rate of change of its momentum. Momentum we'll see in a bit in detail. It basically measures the impact of a body. It is the mass times the velocity of a body. And the rate of change of momentum is equal to the net force. Newton's third law states that for every action there is an equal and opposite reaction. Right. Now there's something very special about these 3 laws, which is they're only valid in certain frames of reference, which are called initial frames of reference. We've seen frames of reference when we saw relative motion, so let's look at that in a little bit more detail. A frame of reference generally is decided by a set of coordinate axes. Sometimes we add a clock to each frame of reference as well, so that we can measure time. So let's say this is a frame S, and let's say this is a frame S dash, which has an origin O dash, which has an x and y axis like this. And let's say the frame S dash is moving to the right with an acceleration of 1 meters per second square. Now we've seen earlier that an acceleration of 1 meter per second square doesn't really have any meaning unless we signify relative to what that acceleration is. And in many cases, for example, when I say the speed of a car is 50 meters per second, it's understood that we are saying the speed relative to the earth or relative to the road. In this case, it's not really clear, so I'm telling you that the acceleration of S dash is 1 meters per second square towards right relative to S. Okay, so this is the acceleration with respect to S. So let's look at an object which is at rest. You can assume that this object is on a floor and no force is acting. So let's say the object is at rest. Now let's look at it from the frame S. In the frame S, the object sits at rest. It does not move. If it doesn't move, that means its position is constant, its velocity is 0, and hence its acceleration is 0. And if the acceleration is 0, then a person looking at this might assume that the force on it is 0. This is using Newton's first law only. Newton's first law says that if a body stays at rest, then the net force on it must be 0. If the force on it is not 0, then it would not be at rest. It would be changing its state of motion. So a person standing on the frame S will look at the acceleration of this object. Let's call this object A. We'll see the acceleration of A to be 0 and we'll conclude that the net force on A is 0. Now let's look at the same thing in the frame S dash. Now in the frame S dash is moving towards right with an acceleration of 1 meters per second square. So if I am standing in the frame S dash, it would seem to me that this object is moving towards left with an acceleration of 1 meters per second square. The equation I've used is the acceleration of A relative to S dash is equal to the acceleration of A relative to S minus the acceleration of S dash relative to S. The acceleration of A relative to S, these are vector equations by the way. The acceleration of A relative to S is 0. The acceleration of S dash relative to S is 1 meter per second squared towards right. So the acceleration of A relative to S dash is 1 meter per second squared towards left. This was the purely mathematical way, but I hope you can see that by intuition as well. If I'm running towards a wall at a speed of 1 meters per second, then it would seem to me that the wall is coming towards me at a speed of 1 meters per second, right? Makes sense. So this man standing in the frame S dash will see that the acceleration is 1 meters per second square. And since the body is accelerating, that means it is changing its state of motion. The force on it must be non-zero. Again, we are not dealing into second law yet, we are just dealing with the Newton's first law. So the first man looks at the acceleration to be 0 and concludes that the force is 0 for the object A. Another man for the same object A measures the acceleration and it's not 0, and from that he concludes that the force is not 0. Both people have used Newton's first law and both of them have come to a different result. We can understand the acceleration being different in different frame because after all acceleration is relative, right? So as you change the frame, the acceleration relative to that frame must change. But force is not relative. Force is measured by, for example, you can hang a spring balance and you can weigh something. So force measured is never relative. So one man measures the force and sees it to be 0. The other man measures the force and sees it to be non-zero. Obviously both of them cannot be true at the same time. One of these is true and one of these is false. So the truth is that this would be called an inertial frame of reference. Why? Because it's at rest or it's not accelerating, and this would be called a non-inertial frame of reference. So inertial frames of reference are those frames of reference which are not accelerating, and non-inertial frames of reference are frames of reference which are accelerating. But this is a trickier concept than it seems at first, because when I say inertial frames of reference are those which are not accelerating, I have to say that relative to something as well, right? So this is what we do. We choose one inertial frame and we nail it down. So let's say we've chosen a frame S double dash and we label it to be inertial, right? So we choose one frame and we call it inertial. This is after all arbitrary, and the reason this is arbitrary is because of Galileo's statement, which is that there is no absolute rest or motion. You can say that the body is at rest or you can say the body is moving depending on the frame, and obviously there is no universal frame. There is no one correct frame from which you'll get all the correct answers. So we take one frame, any one frame, let's say it's the earth or let's say it's a car, and we call that an inertial frame. And any frame which has an acceleration 0 relative to this frame is also called an inertial frame. And any frame which has an acceleration non-zero relative to this frame is called a non-inertial frame. So let's say I take a car accelerating at 1 meters per second squared to be an inertial frame. That means a truck accelerating in the same direction as 1 meter per second square, or a train, or any other frame which is accelerating in the same direction with the same magnitude will also be an inertial frame, and any other frame which is moving in any different acceleration will be a non-inertial frame. Right? Now a thing to keep in mind is I'm talking about acceleration. Inertial frame is defined by acceleration. So if S dash is inertial, then S is inertial because it has acceleration 0 with respect to S dash. S dash is non-inertial because it has an acceleration of 1 meter per second square with respect to S or with respect to S double dash. What about a frame which is moving towards right with a constant speed of 1 meters per second? Well, a frame moving towards right with a constant speed will have an acceleration of 0, and so it will be an inertial frame. So if we take a car moving at a constant speed to be an inertial frame, then every car moving at any constant speed will be an inertial frame because all of them will have an acceleration equal to 0. Right? So this is a key concept. Let's say I take the earth to be an inertial frame. Then a car moving at a constant speed will have an acceleration 0 relative to the earth, so it will be an inertial frame. Whereas a car that is accelerating will not be an inertial frame. Okay, and we can see that it sort of makes sense because force is related to the acceleration. If acceleration changes, then force changes. But if the acceleration of a frame relative to another frame is 0, then the force in those frames will be measured to be the same. So we will not have any discrepancy in Newton's laws of motion. So this is the first law of motion we saw, which is a body will remain in a state of rest or uniform motion unless and until an external force is applied. Right. Now there's one small concept left in this place, which is how do we nail our very first inertial frame of reference? So the earth strictly is not an inertial frame of reference, but it is because it is moving, right? But we can calculate the acceleration of the earth by virtue of its rotation as follows. Let's say this is the earth rotating with an angular speed omega, and this is the radius of the earth re, right? So a particle standing on the surface of the earth will have an acceleration. The reason it will have an acceleration is because it's moving in a circle, and we've seen in kinematics of circular motion that any object which is moving in a circle will have to be accelerated because the direction is changing. And if it's moving at a constant speed, which it is, we can assume that the earth moves at a constant rate. Then the acceleration towards the center is v square by r, which is called the centripetal acceleration. We saw that earlier. That also turns out to be equal to omega square r, since omega r is equal to v. We've seen this in circular motion. So the acceleration can be calculated as omega square r. Now omega can be calculated because the time taken by the earth to travel 2 pi radians is 24 hours. So it will be 24 hours times 3600 seconds. You square this and you multiply it by the radius of the earth, and it will come out to be approximately 0.034 meters per second square. Just to put that in context, gravity is 9.8 meters per second square. So we see that though the earth cannot strictly be qualified as an inertial frame because it is rotating, the acceleration by virtue of the rotation is very small. It is 0.034 meters per second square, which is almost negligible. In fact, if you compare it to the acceleration due to gravity, it's very small. So for the purposes of this course, we will assume the earth to be an inertial frame of reference. So we've done half the job already in deciding whether a frame is inertial or not. We've nailed down our first inertial frame of reference. We'll assume the earth to be an inertial frame of reference. That means the road is an inertial frame of reference. That means any car at rest is an inertial frame of reference. That means any car moving at a constant speed is an inertial frame of reference. Any car moving at a variable speed or at a constant speed but in different directions will not be an inertial frame because it will have an acceleration, right? So this is another important concept, that we just assume the earth is an inertial frame because we've calculated that its acceleration by virtue of its rotation is quite small. So the error will be negligible. So we assume the earth in our course to be an inertial frame of reference, and after we've decided this, we can be able to calculate whether any other frame is inertial or not, right? In the next video, we'll start with Newton's second and third laws of motion and see how to solve problems involving Newton's laws. Thank you.